Assalamualaikum warahmatullahi wabarakatuh and a very good day to all my panels, Dr. Muhammad Azmin bin Abdul Ghani and TS Dr. Nik Rosalina binti Nik Rosli. My name is Aina Atiqah binti AZLAN and my supervisor is PUAN LEHA binti Abdul Rahman. Today, I will be presenting my FYP1 proposal, which is investigation on the effect of starting material size on the production of SiC from rice husk. For the introduction, silicon carbide SiC nanostructures is one of the most important structural ceramic in this world. This ceramic is used in most of applications that involve in engineering due to its excellent properties. Some of the properties are good corrosion resistance, high hardness, and high melting temperature. Due to the excellent properties, it is possible to produce industrial applications such as nuclear fusion reactors, high temperature heat engines, and chemical processing industry. Even though they have great properties, the cost to produce the applications in the industry is quite high. So, some of the applications production are limited. Nowadays, the SiC materials were produced by using the HUSK process. HUSK process is based on carbothermal reduction of silica by carbon in an electric arc furnace. Nevertheless, this HUSK process is based off an outdated technology which requires high-cost raw materials, excessive energy inputs, long reaction times, and as well as products that require further processing before the intended applications. Other than the HUSK process, these SiC materials also can be produced by other few methods such as by reduction of methyl trichlorosilane, by reacting metallic silicon and coal tar pitch mixture, and also by thermal decomposition of potentially inexpensive agricultural waste such as rice husk. Since the HUSK process are costly, the other method that is suitable to be used to produce SiC materials is by doing thermal decomposition of rice husk. This is because the method is low in cost, efficient, and economic. Hence, in this work, SiC was synthesized by pyrolysis of rice husk by using some simple and low-cost equipment. For the problem statement, silicon carbide (SiC) is one of the non-oxide ceramic materials that have been recognized by the world for able to produce strong and tougher composite ceramics and light metal alloys for structural products. With their good properties, the applications produced for the industry are limited due to high cost of production. Therefore, rice husk was used as the starting material to obtain the SiC materials. Rice husk is an agriculture waste material that are available at places that grows rice. During the growth of rice grain, the natural sheath, which are the rice husk, was formed on it. It was removed from the rice grain during the refining of rice. These husks do not have any commercial interest. A large amount of rice husk, which also known to have a fibrous material with high silica content, will be available as waste at the rice milling industries. When this raw material went through combustion under moderate temperature, it produces white ash that contains 87 to 97% of silica in an amorphous form and some amount of metallic impurities. Next, the objectives of this project is to investigate the effect of size of starting material on the production of SiC. The second objective is to evaluate the morphology and the physical properties of the ceramic materials, including the SEM or EDX, density, and XRD. Next is the scope of the project. The scope of this project is to investigate the effect of starting material size on the production of SiC from rice husk. The rice husk will undergo pyrolysis process to turn them into black ash. There will be two different temperatures used during the pyrolysis process. The rice husk will also be burned in an inert atmosphere. Then, the SEM or EDX and SRD machine will be used to analyze the morphology and the properties of the material. Moving on to literature review. The first literature review is pyrolysis of rice husk to obtain SiC ceramic material. There are a few methods that can be used to obtain the silicon carbide material. Due to its excellent properties for industrial application, most of the applications were limited in production because the cost of production is high. This disadvantage has led to intense research on finding the alternative sources of silicon carbide that are low cost and renewable. Therefore, rice husk has emerged as one of the promising candidates due to its finely dispersed carbon and silica that are in intimate contact. It is also exhibit high activity with one another. Lee and Cutler were the first to have successfully synthesized SiC from rice husk in the early of 1970s. Eventually, there were several experimental studies that had been carried out on the synthesis of silicon carbide from rice husk by using different methods and approaches with a lot of success. The synthesis of silicon carbide (SiC) by pyrolysis of rice husk was carried out in a tube furnace. In order to convert the organic materials, such as cellulose, into amorphous carbon, the samples were prepared by first cooking the rice husk in a muffle furnace at 700 degrees Celsius for 10 minutes. After cooking the rice husk, the first sample was taken and milled for 3 hours in a Frisch pulverized 6-ball mill using 20 mm diameter stainless steel balls at 200 rpm. This sample was labeled as ball milled. Then, the second sample was ground by hand using a mortar and pestle. The second sample was then labeled as hand ground. Meanwhile, the last sample was just as received after cooking. A mass of 5 grams of the prepared samples were each pyrolyzed at temperature of 1000, 1300 and 1500 degrees Celsius. The heating rate of the pyrolyzed was 10 degrees Celsius per minute from room temperature to the desired temperature. The time of pyrolysis was also varied at 60, 90, and 120 minutes. This is to determine which sample feature will yield the most SiC. It is also to determine at which conditions of temperature and time the samples would yield the most SiC materials. The process was done under an argon atmosphere. The constant flow rate of 2 liters per minute is used in order to obtain the formation of silicon carbide from carbothermal reduction silica by carbon. The second literature review is morphology analysis. Figure 1 above shows the SEM images of the rice husk that have been pyrolyzed at 1500 degrees Celsius for figure 1A and 1B. For figure 1C and 1D, The rice husk was pyrolyzed under 1700 degrees Celsius. Meanwhile, figure 1E and 1F, it was pyrolyzed under temperature of 1800 degrees Celsius. At 1300, 1400, and 1500 degrees Celsius, the presence of silicon carbide was not observed, but only silica, mostly in the form of cristobalite. It was clearly observed that the SiC formed from the rice husk had two definite morphologies, which are whiskers and particles. Between the 1600 and 1700 degrees Celsius, it can be observed that SiC formation was mostly in the form of whiskers. There was a decrease in whiskers formation at 1800 degrees Celsius, and also the particulate SiC have appeared. According to R.V. Krishna Rao, when the temperature of pyrolysis is increased, the formed filament tend to recrystallize. Then, the product becomes predominant in particulate form. The SiC whiskers formation seems to reach a maximum in samples pyrolyzed at 1700 degrees Celsius. R.V. Krishna Rao showed that there are competitive processes during the pyrolysis of rice husk, which are the crystallization of amorphous silica, the crystallization of amorphous carbon, and the reduction of SiO2 to form SiC particles and whiskers. Nowadays study, the crystallization of the amorphous silica was observed at temperatures around 1300 to 1500 degrees Celsius. Meanwhile, the reduction of SiO2 to form SiC occurred at above 1500 degrees Celsius. The rate of SiO2 liberation and the rate of SiC formation were probably low at 1700 degrees Celsius, favoring the formation of SiC whiskers. When the temperature increased, the rates of SiO2 release and SiC formation were probably high. It also favored the formation of SiC particles. The third literature review is Physical Properties Analysis. Figure 2 presents the XRD spectra for the three samples that have been pyrolyzed at different temperatures. There was no sight of silicon carbide formed at 1000 degrees Celsius for all samples, but there was a silica peak observed at 2 degree equals to 26.8 degree for hand ground and ball mill samples. The peak observed is the amorphous silica that crystallized and transformed to its high temperature state beta cristobalite. Meanwhile, the as-received rice husk that have been pyrolyzed at 1000 degrees Celsius was completely amorphous with no remarkable crystalline phase. This could happen due to the coarse nature of the starting materials, where the surface area of the rice husk was not adequate for chemical reaction to produce at this temperature. A new silica peak was observed at 2 degree equals to 35.8 degree for all samples, when the temperature was raised to 1300 degrees Celsius. This implies that more silica had crystallized due to an increase in temperature. It is worth the observation that the formation of SiC only started to form at 1300 degrees Celsius for all the three samples, even though in small quantities as evident from the short XRD peaks. The low yields is maybe due to the temperature of pyrolysis is low, which does not enable for adequate chemical reaction between silica and carbon in the rice husk. The peaks for both silica and SiC were increased as the temperature was increased to 1500 degrees Celsius. Next is the methodology for this project. We start with the pre-treatment and then we go to pyrolysis process. After the pyrolysis process, we will analyze the rice husk through morphology analysis and also physical properties analysis. The morphology analysis will be analyzed using the SEM or EDX. For physical properties analysis, we'll be using the XRD and density. During the pretreatment, first the rice husk will be washed with water to remove any dirt or any other contaminant that exists in them. Then dry the rice husk for a few hours under a sun or by using oven until it completely dry. The dried rice husk was analyzed under the XRD analyzer to determine the crystallinity of the rice husk constituents. The SEM microscope is also used to analyze the morphology of the dried rice husk before going to pyrolysis. For pyrolysis process, there will be two steps involved. The rice husk will undergo pyrolysis at temperatures starting from around 350 to 900 degrees Celsius first, in order to produce black ash from the rice husk. The second step is the rice husk ash will be going through another pyrolysis where the temperature will be set around 1200 to 1650 degrees Celsius. The pyrolysis process will be done in an inert atmosphere. The pyrolysis of the rice husk will be carried out in a tube furnace. For morphology analysis, we will be using SEM or EDX. SEM is a scanning electron microscopy where it gives out a detailed high-resolution image of the sample by rastering a focused electron beam across the surface. It also detects secondary or backscattered electron signal. Meanwhile, EDX is an energy dispersive X-ray analyzer, EDX or EDA. It is used to provide elemental identification and quantitative compositional information. Therefore, the microstructure of the SiC ceramic material from the rice husk ash will be observed using either SEM or EDX equipment. For physical properties analysis, we will be using XRD. XRD is X-ray diffraction analysis, where it's a technique that is used to determine the crystallographic structure of a material. XRD will measure the intensities and scattering angles of the X-rays that leave the material by irradiating a material with incident X-rays. XRD is also used for the identifications of materials based on their diffraction pattern. So, XRD analysis will be used in this project to identify the existence of the SiC ceramic material in the rice husk ash. For densities, the density of the rice husk before the pyrolysis and after pyrolysis at some temperature will be taken. The density measurement will be done by pycnometer, pear-shaped with ground capillary stopper. The determination of weight loss of sample will be performed in a muffle furnace. For the expected result, at the end of this project, the optimum size in affecting the final product of SiC can be estimated. The morphology and physical properties of the rice husk ash also can be observed. The result may be differ from the past research after the test had been done. This could occur due to the type of atmosphere the pyrolysis takes place or the type of rice husk used. Based on the past research, the density of the SiC increased as the temperature of the pyrolysis increased. The silica content also will increase when the temperature is increased. Table 1 shows the content of density and silica and calcined rice husk from the past research. Meanwhile, for figure 4 shows the XRD pattern of SiC prepared from the hand-ground rice husk ash pyrolyzed at 1450 degrees Celsius, 1500 degrees Celsius, and 1550 degrees Celsius in an argon atmosphere from past research. Based on the result from the past research, I hope that my result will be better than the past research result. That is all from me for my FYP1 proposal. Thank you for watching my presentation. Any inquiries, you can email me at the email in the slide. Thank you.